Hello everybody and welcome back. We're looking at question 22 on our 2016 Pascal paper. There are N students in the math club at Scoynes Secondary School. This is of course named after the very well-known Ron Scoynes, who worked at Waterloo for quite a period of time. When Mrs. Fryer, Fryer is the name of a math contest at Waterloo, but also the name of Ken Fryer, who worked at Waterloo. So it's a very fun little sort of in-joke question so far. Anyway, when Mrs. Fryer tries to put the N students in groups of 4, there is one group with fewer than 4 students, but all the other groups are complete. So I know N is not a multiple of 4. Okay, maybe it leaves a remainder of 1 or 2 or 3. I don't know yet. When she tries to put the N students in groups of 3, there are 3 more complete groups than there were with groups of 4. So more than complete groups of 4. And there is, again, exactly one group that is not complete. Okay. So N is not a multiple of 3. Fine. When she tries to put the students in groups of 2, there are 5 more complete groups than there were with groups of 3. And there's, again, one group that is not complete. So N is not a multiple of 2, and that really sort of narrows it down. It's got to be an odd number there. The sum of the digits of the integer equal to n squared minus n is. So it seems like we have enough information to figure out what n is. Okay. Now, when we're talking about, let's get the previous question out of there. Now, let's focus on the groups of 2. So n is some multiple of 2 plus 1, and k is the number of complete groups. At least complete groups of 2. Okay. But we know when it came to groups of 3, there were 5 fewer groups. And then plus some amount. I don't actually know that number, but I do know this has to equal n. And so I suppose we could equate the two in some way. And maybe try and get a handle on this same amount here. So 3k minus 15 plus... It's going to be, let's call it r for remainder. And r is 1 or 2. It can't be 0. Okay. And so then I guess we could say 16 is equal to k plus r. Bring the 2k over to the other side. Okay. And then there were even less complete groups when we were talking about groups of 4. There were 3 less, because there's 3 more when we're talking about groups of 3. So, and also looks like 4, k minus 5 minus 3 will be k minus 8, plus another remainder, s. And s is 1, 2, or 3, but I don't know which. Actually, I know it can't be 2, because otherwise n would be even. So s is either 1 or 3. Okay. Where could we go from here? Well, I suppose we could do this same sort of rearranging work. Okay. And we could say 33 is equal to 2k plus s. Okay. Doesn't exactly help. Oh, if s is equal to 1, then 33 is 2 times 16 plus 1. And so k would be 16, but taking that and plugging that in here would tell me r is equal to 0, and that's not allowed. So s must be 3. So if s is 3, then subtracting 3 from both sides, we get 30 is equal to 2k. K is going to be equal to 15. This is enough information to get n, but let's also just quickly double check if that's the case. So k is 15. I know k plus r is 16, so r is 1. That is absolutely allowed. And so n should be 2k plus 1, so n should be 31. All right. So n is 31, and what did we need to work on from there? We needed... Oh, sum of the digits of the integer equal to n squared minus n. So 31 squared minus 31, well, that's 961 minus 31, and that'll be 930. And the sum of the digits, 9 plus 3 plus 0, is 12. Is 12 one of our answers? Absolutely it is. So we bubble in B, and we move right along to question number 23.